Okay, today we are going to talk about the Fourier Transform. Okay, so what is Fourier Transform? Last time we talked about the Fourier series. Well, actually, that is for the periodic signals. Okay, if the signal is periodic, then we can use a Fourier series to represent that signal. But most of the time, your signal is not periodic. And in your real life, the signal is not periodic. So in this case, what should we do? If the signal is not periodic, we can also think that actually it is periodic, but the period is infinity. So the period goes to infinity. And in this case, then we consider that infinity. So here is a Fourier transform. And for the Fourier transform, actually, let me tell you the result first. Actually, they'll tell you what frequencies exist. In a signal. Let's see. We will talk about the continuous time Fourier transform, and later on in 2 weeks, then we will talk about the discrete time. For the continuous time, the Fourier transform is your signal times the basis. You can also think about your signal. How do you get the signal? Your Fourier transform times the basis. Similarly, or you can think about this is the coefficient, then you times the basis. Every time you in the product, the basis, again, A is 5i plus 4j. To get 5, that'll be A in the product I. Okay. Similarly, you can think about this. Here is the Fourier transform, and this one is the inverse. So, based on this Fourier transform, let's see if I switch if I reverse the omega x. If I have minus omega, then let's see what happened. If I have a minus omega, well, just changing the variables. So here we have x e to the j omega t. Right? Because now omega becomes minus omega. So here becomes minus omega. We have a minus. So that's why we have omega here. Then dt. This will be the Fourier transform conjugate. Same Fourier transform, but we do the conjugate. So if you conjugate that, here you conjugate. So that's why you have e to the j omega t. And this equals x minus omega. In this case, that's not straight. In this case, let's see the magnitude. The magnitude is equal. The magnitude of the Fourier transform and the magnitude of the reverse frequency, they'll be the same. So the magnitude, that is the even function, But the phase, well, the phase is, here we have minus the odd function. If I plot the transform, here is the real, here's the real part, and this is the imaginary part. And this is the Fourier transform. Here we have theta. Then this one is x minus omega. Oh, actually, I should write it down. This is x conjugate. Same thing. Okay, so the magnitude is an even function, but the phase is an odd function. Let's see some examples, and we'll continue. And those are, I'll say, classic one. First, what is the Fourier transform of a rectangular pulse? It's not the train of rectangular pulse, right? So this is very epic. You should know the result. So x is 1 between minus 2 and 2 when t between minus 2 and 2. What is the Fourier transform? First, let's just use the definition. X omega. Think about your signal times inner product the basis. Your signal inner product the basis, you'll get kind of like a coefficient. Let's see, x a1i plus a2j. a1 will be x in the product, your basis. Here is also the basis, dt. I only have a values between minus 2 and 2. So here's 1 e to the minus j omega t dt. So here we have 1 over omega e to the j omega t minus e to the minus j omega t divided by j. Then this is 2 times sine 2 omega divided by omega. So what is this? A sinc function. So a rectangular pulse in the frequency domain, that will be a sinc function. Let's plot the sinc function. The magnitude, well, the magnitude when x equals 0. You'll get 4. You can take L'Hopital's rule, 2 times 2 cosine 2 omega divided by 1. You get 4. So here we have 4. That's the peak, because x of 0 is 4. And when we get 0, when omega equals pi over 2 minus pi over 2. And then next one, that's pi minus pi. Because we need x omega equals 0. So sine 2 omega equals 0. Your omega should be m pi over 2. So now a rectangular pulse, the Fourier transform is sinc function. Let's see a general case. For the general case, we have a magnitude A, and the period is from minus t over 2 to t over 2. Then this is your Fourier transform. That's a sinc function. What is the peak? And how about this knot? When will we get 0? Let's see. Suppose we have a general term, this one, and then your Fourier transform is x times their basis. Okay, and then we only have values from minus t over 2 to t over 2. And then the magnitude is A times the basis. Then you get A over j omega e to the minus j omega t. And your t is from minus t over 2 to t over 2. So you get minus j a over omega e to the minus j omega t over 2 minus e to the j omega t over 2. And here we have a sine function, minus j a over omega and minus 2j times sine omega t over 2. Which is 2a over omega. And we have a sine omega t over 2. And we want to write it as a sinc function, so we have a t a sine omega t over 2. And in the denominator, we also need the omega t over 2. Because this is a sine function, a sinc function. So that's why we have t here. Okay. So here we have the magnitude at and sinc function. Remember that the sinc function is an even function. Okay, then what is the peak? The peak will be 80. And when will we get 0? When will we get 0? Here is omega. When will we get 0? What values of omega? We need right. Let's write it here. Because we need 0, which means sine omega t over 2 should be 0. That means omega t over 2 is m pi. So when omega equals 2 m pi over t, you get 0. So here we have 2 pi over t, and then 4 pi over t, 6 pi over t. Okay, because at this point, omega t over 2 should be pi. And then you'll see the magnitude spectrum. Okay, if you take the magnitude, so everything will be positive. Oh, and also here, that's 2 pi over t, 4 pi over t, and 6 pi over t. That's even function. So, any questions so far? Now let's observe this pair, the rectangular pulse and sinc function. When t becomes bigger, becomes bigger, so that'll be more flat. More flat. If it's in this case, how does it look like? For the sinc function, t becomes bigger. So this t becomes bigger. This value is small, right? So this should be more sharp, right? When t is smaller, so if this is sharp in time domain, then in frequency domain, then this is more flat. Right? So the sharp changes in time, I think I should get t here. Well, you require the wide frequency content. So if I have this sharp one, pretty sharp, then I need more frequency, which is like a more bandwidth, which also means that more money. Let's see the physical meaning of the Fourier transform. Okay. So what is Fourier transform? To have our signal, actually we can have, you can think of this as a coefficient times their basis. Okay. So we have the Fourier transform times the basis. Now we separate to two parts. First, let's integrate from 0 to infinity, and then integrate from minus infinity to 0. So how do we deal with this term, this integral? Let's change the variable. First, let's have omega prom equals minus omega. So in this case, this omega becomes minus omega prom. Okay? Omega becomes minus omega prom. Omega prom equals minus omega. D omega prom will be equal to minus d omega. So d omega becomes minus here. Then if I have minus, that means my integration is from 0 to infinity. Okay? In the beginning, that's minus infinity to 0. And if I have minus sign, that means I will integrate from 0 to infinity. Okay? And then, what else? All right, so that's it here. Then your signal now is two integrals. They are all from 0 to infinity. and we all have 1 over 2 pi. So we take the factor 1 over 2 pi outside, integration from 0 to infinity. Here, the first term plus the second term. Here's the second term. Okay. And you can see this, they are conjugate. Okay. So in this two part, they're conjugate. Therefore, I can have this integration that be 2 over 2 pi integration, and I'll only take the real part of x, the Fourier transform times the basis. And what is the real part? That is 1 over pi. Here we have a like a coefficient times cosine omega t, and then coefficient times sine omega t. And then the omega here is continuous. And from here you can see this is the combination of your sinusoidal waves. So combination the sine waves. So actually here you can see that the signal is consisted of a combination of sine waves. The signal is a mixture of pure oscillations. How come? Oscillations. So the Fourier transform may tell you how much of each frequency is present to form your signal. Okay, so your signal consists of a lot of combination of sine waves. Okay, let's just compute the Fourier transform of the x. That's the exponential decaying times the unit step function. So there'll be your signal times, well, in the product, your basis. And then for signal, that's the unit step function. So I only integrate from 0 to infinity. E to the minus t times e to the minus j omega t dt. You get 1 divided by 1 plus j omega. Actually, you can see the Fourier transform table. Okay, you don't need to calculate that. Okay, you can find it in the Fourier Fourier transform table, and it looks like here's omega. So a signal in time domain that we can see the signal. We'll say what's happening over the time. But in frequency domain, then we can see the what frequencies are inside. Okay. All right. So for the Fourier transform here, let's have some recall. So here, recall from the linear algebra. Actually, we can express a vector, okay, in terms of the basis vectors. The basis vectors. So omega is consisted of the combination of all the bases times their coefficient, right? How do I get this coefficient? Again, your vector in the product, your bases, because they are the bases are orthogonal. Okay. So if I have 1, 2, 3, suppose omega is in 3D. So 1, 2, 3. 1, 2, 3 means that the first, that's 1. The coefficient times the basis here in 3D. So basis is 1, 0, 0. And then 0, 1, 0. And then 0, 0, 1. So the coefficient here is 2 and 3. And this 3 on the basis of R3. Therefore, based on this example, all signals can be expressed as a combination of the basis function. Here we have function e to the j omega t, like here. So we can write it down. A signal x is 1 over 2 pi. Okay, all the combination. So for continuous case, that's the integration. Well, x, not only for the integration, because for the vector functions, when they do the function in the product, then we do the integration. So x e to the j omega t d omega. So this x of omega represents that the signal in the basis of the complex exponential e to the j omega t So here is the Fourier transform. Again, to get those coefficients, how do you get the coefficients? Your signal in the product, the basis. Here, when you do the inner product, we need a conjugate. You can also think about this signal is a combination of the basis function 1 over 2 pi these are the same concept, just like omega equals a 3I minus 2j plus 5k. Omega in the product I, then we get 3. Omega in the product j, we get minus 2. Okay. And then to get omega, it's the combination of your coefficients times the basis. Alright, now let's see some properties, the basic properties of the Fourier transform in continuous time. Here for linearity. Okay, if I take the Fourier transform of a linear combination, actually I can take the Fourier transform individually and do the linear combination. Okay. Next, time shifting. From time shifting, let's see the inverse Fourier transform. You can also think of inverse Fourier transform is to how to express your signal. A combination of the basis function. Okay, so the combination of the basis function. Now, if I shift by t naught, what happens in the frequency domain? If I shift by t naught, then here t becomes t minus t naught. Okay, we have 1 over 2 pi okay, t becomes t minus t naught. So I have 1 over 2 pi. We have e to the minus j omega t naught x omega e to the j omega t omega. Now you have new term here. So if I shift in time domain, what happens in frequency domain? There'll be, this becomes e to the minus j omega t naught x omega. Now see this? That means that in frequency domain, the magnitudes is still the same, right? Because this magnitude is 1. The only difference is the phase change. Okay, they change the phase. So the magnitude is still the same as the Fourier transform of your signal. But the phase, they'll be, well, they just change by omega t naught. Remember, if I have two vectors, if I have two vectors A in the product B, that means the magnitude A times the magnitude B, and then what? The phase will be, suppose the phase for A is theta and the phase for B is phi, then there will be theta plus phi. Okay, so the vector A is the real part plus the imaginary part. That is also equal to the magnitude of A times the phase e to the j theta. And then the vector B is the real part plus the imaginary part. So that's the magnitude of B times the phase. This phase is phi. Remember that for the real part and imaginary part, if I have a vector A, so here is the real part. And this one is the imaginary part. So here is theta. And over here is the magnitude of A. Alright, so now let's see an example. If I have the signal, what is the Fourier transform? Actually, if you plot this signal, you can see that this is a unit step function. Here is a unit step function. So I can also express this signal into the unit step function, which is ut plus the shift by 1, ut minus 1, and then minus 2 ut minus 2. Okay, for ut, this is unit step function, right? But here I will cut it off. So when t minus 2 here, I should have this. Here's ut 1, 2. So when at 2 here, I should go down. So I should have step function going down. But in t minus 1, I also have another unit step function. So 1 plus 1 here actually I have a 2. So that's why I have minus 2 that can cancel out. Okay? Then what is your Fourier transform? This one, you can see that as long as you know the Fourier transform of the unit step function, then that's it. You don't need to do the integration by the definition. Okay. So here's the Fourier transform of the unit step function, and then shift by 1 and also shift by 2. So for the linearity, okay, I can take the Fourier transform individually. Now, if I have a shift in time, what happens in frequency domain? The magnitude is still the same, which means that's the Fourier transform of the unit step function. But the phase changes. So here I have a phase changes e to the minus j omega. Similarly, the magnitude is the same, but here I shift by 2. So I have e to the minus j omega 2. So you have the Fourier transform of the unit step function, 1 plus e to the minus j omega minus 2 times e to the minus j 2 omega. So you can check the table, the Fourier transform table. The unit step function, their Fourier transform is 1 over j omega plus pi delta function, then 1 plus e to the minus j omega minus 2 times e to the minus j 2 omega. Alright, if you don't have any questions, let's just take a break. Next, let's see the frequency shift. We just saw the time shift. So if we have a shifting time domain, then in frequency domain, my magnitude is still the same. I just have the different phase. How about I shift in frequency domain, for example, here, and I shift by omega naught. What happens actually in time domain? So if I shift, which means that omega becomes omega minus omega naught. Okay, so here omega becomes omega minus omega naught. Then we have an additional term, e to the j omega naught t. So here, x e to the minus j, omega now becomes omega minus omega naught t dt. So I have an additional term. What is the additional term? E to the j omega naught t. X e to the minus j omega t dt. So if I shift in frequency domain, that means in time domain, at times the complex exponential. That means I am doing the modulation. Okay, we will see this modulation a lot later. So in time domain, I timed cosine while I hear the complex exponential, but normally we will just times cosine because this is very expensive. So if I times cosine or even sine, what happens in frequency domain? I just shift your signal or your frequency spectrum by omega naught. We will use that a lot later because like in time domain, for example, like when I speak and we have fans rotating, around, walking, and maybe we have some background noise. Okay, everything is together in time domain. You just hear that at the same time. It's really hard sometimes to distinguish your signal or your voice. Then what happens? We can times something, then we can analyze it because when I times something, then I shift in frequency domain. So I can extract my main signal and I do something. Later on, I times the cosine or sine again. They will go back to the baseband. Then you can get or beautify your signal. Okay? So this is very important. In time domain, if I times the complex exponential, which means that I'm doing the modulation. In frequency domain, I just shift. Next, the time scaling. Okay, this is my signal, but if I compress or delete, if I just times AT, okay, could be expand or decrease. Now t becomes AT. So here we have 1 over 2 pi x e to the j omega AT d omega. So now let's change the variables. Let's have omega prom equals a omega. So now omega a here becomes another omega. We say omega prom. So let's put here that omega prom equals omega A, which means omega becomes omega prom over A, and then d omega prom equals A d omega. So d omega becomes d omega prom divided by A. Therefore, here I have 1 over 2 pi. Same integration, integrand here. Omega becomes omega prom over A. Omega prom over A. And e to the j. Omega A is A omega prom T. D omega becomes D omega prom over A. That's 1 over 2 pi. Here I have 1 over A. That's here. 1 over A. And now, since this is omega prom, omega prom, omega prom, let's just write it down as omega. Okay? So, x omega over A e to the j omega t d omega. Right, so now the Fourier transform of the time scaling of the signal will be what? Here. Okay. 1 over A x omega over A. Okay, so based on this time scaling, let's see. If I have a signal and then the Fourier transform is this. Now I compress. Okay, if I compress, what happens in frequency domain? First, let's see how about the magnitude. The magnitude should, if I compress, A is greater than 0, greater than 1, then they will go down, right? And then x omega over A, so A is 2, 3, 4, become wider and wider. Okay, so it should look like this. All right. If you don't have any questions, next let's see the differentiation. So I can express the signal as a linear combination of the bases. When I take the derivative, what happens? That'll be 1 over 2 pi. X. Okay, so here we have d e j omega t dt d omega. Okay. So 1 over 2 pi x omega. So e to the j omega t. If I take the derivative with respect to t, then I'll get chain rule j omega and then the complex exponential. So we have here, every time if I take the differentiation in time domain, then in frequency domain, I will generate the omega. Okay, I'll generate the omega. So every time if I take the derivative, which means that if I take the derivative nth times, so here I have nth derivative, then I have generate j omega n times. Then you may be curious about taking the differentiation in frequency domain. What happens in time domain? Now if I take the differentiation in time domain, then we generate omega in frequency domain. How about the other way around? If I take the differentiation in frequency domain, what happens in time domain? Looks like we have kind of like a similar pattern for that. Right. Let's see. If I take the differentiation in frequency domain, now here it is x d over d omega e to the minus j omega t dt. So you have xt and then minus jt e to the minus j omega t, right? So here. Minus j t x. So if you take the differentiation in frequency domain, then in time domain, we just times the time t. Well, because in time domain, we don't like this imaginary part. So here we can write it down. It's just like generate time. Here we can have j in frequency domain. All right, next is the integration. If I take the Fourier transform of the integration in time domain, then in frequency domain, we have two parts. Remember that when we take the we're trying to find the solution of the ordinary differential equation, right? And then the particular solution or the equation is non-homogeneous, and we have this part for the forcing term. Well, that's really hard to find that in time domain. That's what should we do? That's why that we take the Fourier transform, okay, to the frequency domain and try to find a solution, because this is not the closed form. Next, the Parseval's relations. What is the Parseval's relations? This relationship, we will say that from this equation, we know this is the signal energy, and here is the energy of in frequency domain. The energy should be the same. So this is This is the signal energy. And the right hand side is the energy, but I will need to times 1 over 2 pi. Okay, because we use the omega, so that every time we have like this 2 pi term, sometimes 2 pi or 1 over 2 pi. But for some textbook or in physics, their definition for the Fourier transform is using the frequency f, not the radius per second. Then in that case, they will cancel that 2 pi term. But whatever we use for the Parseval's relationship, we need to know that the energy in either in time domain or frequency domain, it should be the same. So here is a note: the total energy of the signal is here's the magnitude, then it is just x squared t dt. If x is real, then for conjugate, this conjugate is still real, okay, because we don't have the imaginary part. Then what happens to the total energy? For the total energy, okay, this is xt, x conjugate t. So this is xt. I do the conjugate. When I do the conjugation, then there will be x conjugate and e to the minus j omega t. Okay, so here we have x conjugate x, and then we put 1 over 2 pi outside, e to the j omega t, d omega dt. For this double integration, let's see this part. What is this integration? Signal in the product, the basis, that is that you can think about this as a coefficient or the Fourier transform. Okay, so here is the Fourier transform. Fourier transform and their conjugate. This is 1. So you can see that the total energy, it should be the same. The difference is that here we have 1 over 2 pi. So this is the signal. Suppose the Fourier transform looks like a triangle. Now if I square it, that's the energy. If I take the integration, what does that mean? Taking the integration, this energy is under this area, right? So here is the area. Right, so this is area 1. Now in frequency domain, okay, this is also the energy. If I find the, if I take the integration, that means I'm trying to find the area under this curve. Okay, this is area 2. So actually they should be equal, but I need to times 2 pi here. Alright, maybe your time. What is the energy of the signal? X. We only know that the Fourier transform looks like this one, like a castle. Then what is the energy of the signal? Alright, actually you just need to find the area. Okay, but you need to divide by what? 2 pi. Okay, so If you want to find the energy of the signal, you can also see that in the frequency domain. Okay, it's the same from the Parseval's theory. So x, actually this is equal to 1 over 2 pi x omega, omega, the magnitude. So under that area, we have 1 over 2 pi from -2 to -1. That's 2. So 2 squared. And then from -1 to 1. And from 1 to 2, we have 2. So the area is 10. So divide by 2 pi, you should have 5 over pi. Next, the property is symmetry. Okay, so suppose x, this signal is real valued, which means that if I take the conjugate, it doesn't matter, it's still just the signal. Then if I take the conjugate of both sides of the Fourier transform equation, so if I take the conjugate minus becomes positive. So here, then we replace omega by minus omega. So here it will be minus omega. Therefore, we get x conjugate minus omega, that'll be equal to, because the signal is real valued, so here it is still x over t, e to the minus j omega t dt. So you can see that if I take conjugate and reverse, they'll be equal to my original Fourier transform. Or we say that if I reverse it, the Fourier transform, that will be the conjugate of your original one. So if we express that in polar form, how does it look like? X omega in polar form, I need the magnitude and the phase. So the magnitude and the phase. And how about x conjugate? Here. So what is the magnitude? This magnitude x minus omega. And how about the phase? We also have x minus omega. And x is the real valued. So for x real valued, they should be the same. So the magnitude is still the same. Which means the magnitude is an even symmetric. And how about the phase? The phase is odd symmetric. Okay, next, let's talk about the convolution. And I think that when you learn, the Fourier transform is in this semester, right? Maybe some of you have already learned that. But if you are junior or senior, that you learn the advanced mathematics, engineering mathematics, so you probably know what's going on about the convolution. But here, let's just still talk about it. What is the convolution? This is a convolution, right? The convolution in time. The convolution in time domain, that means the multiplication in frequency domain. Okay, let's prove it quickly. So, if I take the Fourier transform, what happens? Yeah. Okay, so this is my function. And I take the Fourier transform. Okay? You can just think about this is a function, say h. Now we have the double integration. So let's rearrange this integration. Let's deal with the dt first. So let's put everything with tau outside. Then we have ft minus tau e to the minus j omega t dt and d tau. What happens if we have a time delay? What is this? If I have a delay in time, what happens in frequency? Right. So if I have a time delay in frequency domain, magnitude is the same, but I have a phase difference. So for the phase difference is the complex exponential. So this is a Fourier transform times the phase difference. Okay, now we are doing the integration with respect to tau. So I can put this Fourier transform outside. So I put the Fourier transform outside. And then g of tau e to the minus j omega tau d tau. Function in the product, the basis, you get the coefficient, which is the Fourier transform of g. Right, now the other way around, if I have a multiplication in time domain, what happens in frequency domain? Then in frequency domain, I do the convolution, but I have a factor 1 over 2 pi. we use this a lot. Like in time domain, we do the convolution, but in frequency domain, we do the multiplication, especially in the LTI system. Okay, so if I have a signal, send it to the system. Then what is the output? The output is signal convolved the system. So if I want to find the Fourier transform of the output, then that's the Fourier transform of the input convolved the system HT. So actually they can do the multiplication. And then you can get your output in time domain by taking the inverse Fourier transform. So let's review the LTI system's property. I have a signal. I send to the system, the first system, and then concatenate with the second system. Then I got the output YT. I can combine these two systems. Actually, there'll be H1 convolved H2. Seems like for the system property and also the convolution, I can switch. So you can also think I send a signal to the second system first, and then send it to the first system. I still get the same output Y. This is in time domain. How about in frequency domain? It's similar. Let's say in frequency domain. In frequency domain, the output is X times H1 times H2. You can also think that the signal is sent to a bigger system, omega 1 times omega 2. So that also means I can send the signal to the second system first, and then followed by the first system. So let's consider a system's impulse response H. If I have an impulse response H, and then the Fourier transform of this impulse response is H of omega. That's the frequency's response. So frequency's response is this. We have already seen that before, right? That's the Fourier transform of your impulse response. So in time domain, we do the convolution. In frequency domain, we do the multiplication. So the y is x times h, the system's response. And if we have the delta function, remember that how do we know the system? The x, and I have a system, the y. If I don't know that system, what should we do? Send the delta function to that. Then you can get h, right? So let's see. The Fourier transform of the delta function is 1. Then I can get the frequency response right away. You can also think that for the if you derive it, the delta function, if I take the Fourier transform, that's delta t e to the minus j omega t. The delta function, I only have a value 1 when t is 0. So which means this t should be 0, minus j omega 0. So overall that's 1. So we can explain that in time domain, I send the delta function, I can get the impulse response right away. Similarly, in frequency domain, because the Fourier transform of the delta function is 1. So if I send 1, then I got the frequency response right away. Well, let's see some examples. So here, I have an impulse response. I want to find this. Well, find the Fourier transform, or you can say that I want to find the frequency response. Well, just take the Fourier transform. Okay, we will do that quickly because that's not that hard. So for the Fourier transform, the first one, e to the 2t. Unit step function, and we have time shift and also time shift. First, what do we do with the first term? Or we just times the exponential. Okay, so we have e to the minus 2t ut Fourier transform, so e to the minus j omega t dt. And the second and third term, it's just like unit step function and a shift. You can either check the table or you really do the integration. Okay, I just give you the answer. Okay, we won't focus on too much time on this. It's just like a routine calculation. All right. Next, I have an input 1. And the impulse response delta function, shifted delta function. What is the output? You can have x convolve h. We can also use the convolution property, because here you see that 1 and delta function, we know the Fourier transform. I think this should be easier. So, and also that we want to find the Fourier transform of the output. So here we can get the output in Fourier domain, that's the multiplication of your input and also the system response. So that's the Fourier transform of 1 delta function Okay. If it is 1, then, well, you can check the table or you redo the integration. We have 2 pi delta function times, since I shift in time domain, in frequency domain I have a phase difference. Here is the exponential to the minus j omega t naught. Next, that is the output. Then what is the frequency response of the LTI system? So what is the frequency response of the system? This means h over omega. Okay, so I want to find the h over omega, the system's response. What should we do? Let's see, we have a system. Okay, so if I take the Fourier transform of the system, as dx over dt. Remember that if I take the differentiation in time domain, what happens in frequency domain? I generate the omega. Okay, so every time I generate the omega, so we can see that this is the frequency response times the Fourier transform of x. So your frequency response is j omega. And for the LTI system, we have the relationship between the inputs and outputs, okay, by the differential equations here. Okay, then what is the frequency response? Again, what is h over omega? This is our differential equation. Then we need to take the Fourier transform. Okay, so if I take the Fourier transform, okay, here we have kth derivative, and the right hand side still kth derivative. For the property of the linearity, so we can take the Fourier transform inside. So when I take kth derivative of the signal and then take the Fourier transform, each time I will generate j omega. So kth times I will generate j omega to the power k. Similarly to the right hand side, okay, here you can say this is by linearity of a Fourier transform. So you will get j omega to the k, and then right hand side j omega to the k. So you can get your frequency response. Okay. All right. Also remember, if I take the Fourier transform of the kth derivative, then I generate j omega k times Alright, now if I have the differential equation, ODE, okay, I need to find the output. Okay, this is just like a quick review of your engineering mathematics. Okay, you can guess, you can set it 0 to find the homogeneous solution, and then with the x to find the particular solution, and you combine these two to get your overall general solution. Or you can take the Fourier transform to do it. But if you take the Fourier transform, let's see, if I have the exponential times the unit step function, you can check the table, and then you will see e to the minus alpha t unit step function. Their Fourier transform is 1 over alpha plus j omega. So how do we find the output y in time domain? First, we can find the y in frequency domain. And then, if you use the inverse Fourier transform, then you find the output in time domain. You can follow this table, okay, alpha equals 2. Or if you quickly find the Fourier transform here, there will be e to the minus 2t ut, and then basis. Because it's a unit step function, so I only have values from 0 to infinity. E to the minus t 2 plus j omega dt. So you get 1 over 2 plus j omega. Now let's take the Fourier transform on both sides. When you take the Fourier transform, okay, here's the derivative. Every time you will generate j omega. So you will get y omega equals x omega divided by j omega plus 4. We also have x omega, so that is 1 over j omega plus 4. And then your x is 1 over j omega plus 2. So using the partial fraction, I have j omega plus 4 and also j omega plus 2. Here we have a and b. Now you can see we can expect that my y in time domain will be a 4, that's alpha, times e to the minus 4t ut plus b, same thing. Okay. alpha will be 2. So here you should have the form. The y is a e to the minus 4t ut plus b e to the minus 2t ut. How do we find a and b? So using the partial fraction, find a and b by partial fraction. So 1 will be 2 plus j omega times a plus 4 plus j omega times b. So you'll get j omega equals minus 2. When let's just fill in. Say j omega equals minus 2. Then this 0. I got b. So b is 1/2. If j omega equals minus 4, then a is minus 1/2. Now you can, I don't have space, I'll bring this back to here. Okay. Last property, that's called duality. Have you thought about that? If I take the Fourier transform, now I'm in the Fourier domain, right? But in Fourier domain, that's just a symbol. I can also think about this function as in time domain. Then I take the Fourier transform again. Then what happens? Okay, so now this is in Fourier domain. Okay, now I just change the dummy variable to lambda. Okay, so I can change, this is dummy variable, so I can use any kind of symbol. Now in this case, I will replace omega by t. So here there'll be t. And this is the capital X, okay, not the lowercase x. So this in time we have x lambda e to the minus j t lambda d lambda. Now I just divide by 2 pi. So I need to times 2 pi back. X lambda times e to the minus j lambda t d lambda. Next, let me change the lambda to minus omega. So omega equals minus lambda. D omega is minus d lambda. Okay. Then x will be 1 over 2 pi. Lambda is from minus infinity to infinity. So omega is from infinity to minus infinity. Infinity to minus infinity. 2 pi x minus omega e to the j omega t minus d omega. That's 1 over 2 pi here we have 2 pi x of minus omega e to the, or we just switch the integrals. So this is j omega t d omega. From infinity to minus infinity, here we have minus, so we switch. And what is this? you can see that I'm also taking the Fourier transform. So if it is x of t, then I take the Fourier transform again. I will have 2 pi times x of minus omega. So now you can see that if I have a signal in time domain, I take the Fourier transform. Then I have a x, big X or capital X over omega. Then I take the Fourier transform again. Then I will go back to your time function, but it's still in frequency domain, because every time when you take the Fourier transform, that is in frequency domain. But now that is the function of x, the lowercase x, and then they reverse, then times 2 pi. So the formulas for the Fourier transform and the inverse Fourier transform are the same up to a minus sign and a factor 2 pi. That's called the duality. You can still play it, right? Then let's take a Fourier transform again. What happened? And then Fourier transform again. What happened? This we know there will be x, capital X, but what? Now I reverse. Alright. We have another 3 dual properties. Okay. Like if I shift in time domain, then in frequency domain, I have a phase change. Similarly, if I have a, not time domain, if I have a delay, if I have a shift in frequency domain, that means in time domain I times the complex exponential. This is called modulation. The other one is that if I have the convolution in time domain, then in frequency domain I have a multiplication. In other words, if I have a convolution in frequency domain, then I have a multiplication in time domain. The other one is that if I have a differentiation in time domain, then I generate omega in frequency domain. But if I take the differentiation in frequency domain, in time domain I just generate time, t. Okay, next, let's find the Fourier transform of the delta function, because we will use this a lot later. Let's see what we have. If I take the Fourier transform, e to the minus j omega t, but only when t equals 0 we have values. So this will be 1. Since the delta function is 0 when t is not equal to 0. So if you plot it, what do we learn from here? Remember that what is the Fourier transform of rectangular pulse? A sinc function, right? If it is narrow, and narrow, and narrow, what happened? If it is going narrow, then this will be wider, wider, wider. And finally, if I have a pike, then in frequency domain, I have just all magnitude 1. So an impulse has equal energy at any frequencies. Then if this is 1, what is the inverse transform? Inverse transform should be like a delta function, right? But can you do it from your formula? We just know that the Fourier transform of the delta function is 1. But however, if I want to find the inverse Fourier transform, so here we'll put 1 times e to the j omega t d omega. You will get 1 over 2 pi e to the j omega t divided by jt. And then t is from minus infinity to infinity. What is this? We will see that hopefully in 5 minutes. Right, another example. I want to find the inverse Fourier transform of the delta function. Now, here we have delta function. Then what is this in time domain? And also I shift to here. Then what is in time domain? Well, if I shift by 2, at least you can expect in time domain what happens if I shift by 2. In time domain, I do the modulation, right? I should times e to the j 2 t. But what is here? So for the inverse Fourier transform, that's 1 over 2 pi e to the j omega t d omega. When omega equals 0, we have a value, so there'll be 1 over 2 pi. So if I shift by 2, then I should have 1 over 2 pi times the complex exponential. So you should have 1 over 2 pi and then complex exponential e to the j 2t. All right. Now let's see. We can also take the Fourier transform of the periodic signals. If the signal is periodic, we can express that in Fourier series, right? But we may be interested in having the Fourier transform. How does it look like? So if I take the Fourier transform by the linearity, okay, I take the Fourier transform inside. So we need to actually find the Fourier transform of the complex exponential. But here, exponential and exponential, we combine it. And then you take the integration. So we have 1 over j k omega naught minus omega times e to the t k omega naught minus omega. And your t is from minus infinity to infinity. And actually, what is this? Now we can't find it using the integration. Then let's think about the inverse Fourier transform of 2 pi delta function. And we just found it. Similarly here, we shift by omega naught. And then I have a factor 2 pi. So if I try to find the inverse Fourier transform of this one, we get 2 pi delta function omega minus omega naught. E to the j omega t d omega. Only when omega equals omega naught we have a value, otherwise no. So here we have e to the j omega naught t. So you can see that in time domain I have e to the j omega naught t. Then in frequency domain we have 2 pi delta function omega minus omega naught. Then we found it. Here it's omega, and then we have 2 pi here. So you should have too big. This at omega naught times 2 pi. Therefore, for this periodic signal, okay, what do we have? If I take the Fourier transform, ak e to the j k omega naught t, then it becomes k from minus infinity to infinity. I have a 2 pi ak and delta function, shifted delta function. I should have k omega naught. And it looks like omega, and then this is x omega. All right. So for the periodic signal, actually when we take the Fourier transform, well, it becomes a combination of your sterns. Okay. Okay. Let's finish this example. Okay. So if I have a signal, okay, that's sine function, I can also rewrite it using the complex exponential. Then the omega naught will be 2 pi times 440. Then what is the Fourier transform of this? Okay, so here we have sine 440 times 2 pi t, and then times complex exponential, well, the basis, which is equal to the Fourier transform of e to the j 440 times 2 pi t minus e to the minus j 440 times 2 pi t So by the linearity, first term e to the j 440 times 2 pi t, and then the second term, the Fourier transform of e to the minus j 440 times 2 pi t. So here we have 2 pi delta function omega shift by 2 pi times 440. And second one, 2 pi delta function omega shift to the left by 2 pi times 440. So you can see that the A1 is 1 over 2j, and A minus 1 is minus 1 over 2j. And next week, we're going to talk about something very important, the Fourier transform with the sinc functions. What happens that, for example, like 2 sinc functions multiply in time, what happens in frequency domain? We know that for the sinc function, it's this, right? And you need to convolve another sinc function. But what happens in frequency domain? Or if you times together, it's really complicated here, right? If you want to time these 2 sinc functions. But we know that for the sinc function, the Fourier transform actually is a rectangular pulse. But rectangular pulse during the convolution, that will be easier, right?